All right. Good evening, everybody. Uh, Here we are for another live session of the NPTEL course on urban utilities planning, water supply, sanitation, and drainage. One second. Yeah. Uh, the course instructor is Dr. Devapratit Pandit. He is an associate professor at the Department of Architecture and Regional Planning at IIT Kharagpur. I am Monica S. I am a research scholar at the same department. I'm really sorry about the delay that happened today. There was a bit of a technical issue, localized technical issue, so as to say, from our end. So, in this course, we essentially have two means of interaction. One is the doubt clearing session, as well as problem solving session every Monday, 7 p.m. to 8 p.m. Essentially, we look at the solutions for a few problems, and once each problem has been discussed, you can raise your hand, unmute, and raise your query. Questions can also be posted in the chat box. We also have a discussion forum for the course. Any questions related to the live session, also related to the general lectures, can be raised there. They'll be answered in due course of time. So, week 9 majorly delved into sewer design, and a short recap. The first lecture dealt with the design of sewers. Next two lectures with runoff estimation, and the last two lectures of the week on sewerage network design. So essentially, we saw that sewer design depends on both sewage or sewage output from households, as well as the case of stormwater drain, right? Stormwater runoff, especially in case of combined sewer systems. So, which is why we are looking at runoff estimation as well. So, in this live session, we'll be looking at a few of the assignment questions from the previous run of the course. There'll be both theoretical and numerical questions. The thing is, one of the numericals has a slight discrepancy from what was taught and what has been presented. So, right now, I will be presenting the solution that has been suggested by the NPTEL team. However, for that particular numerical, I think I will either get back to you in the next live session whether the answer suggested by them is correct or faulty, or there might be a post in the discussion forum regarding the same. Right. So let's move into the lectures. The first question of the day: self-cleansing velocity depends on A. Particle size, specific gravity of particle and conduit shape. B. Particle size, conduit shape and depth of flow. C. Specific gravity of particle, conduit shape and depth of flow. Or D. Particle size, specific gravity of particle, conduit shape and depth of flow. Any answers? Okay, we have one answer in the chat box. Sir Rahul has said D. And you are right, Mr. Rahul. As we can see from the lecture slides, self-cleansing velocity depends on particle size, specific gravity. If it's water, we take the value 1. If it's grit, with grit, we take the value 2.4 to 2.65. And we also look at conduit shape and depth of flow. So the specific gravity of the particle or the water, the liquid flowing through, is essential because at the end of the day, self-cleansing velocity is addressing what? The capacity of the, say this is a sewer line and there is some deposit. So this is water flowing and there is some deposit that happens. At some point of time in the day, there should be enough velocity or movement of flow of water, flow of sewage in this pipeline, such that this siltation or whatever deposit happens is sort of washed away, which is precisely why the specific gravity of the liquid flowing through comes into the picture. Conduit shape, essentially, again, what happens is the cross section comes into play, right? And the depth of flow. So how much water typically flows through the sewer is also important for calculating this value, right? So the answer is D. Moving on to the next question. So this is a numerical problem. Consider the following data of sewer. The sewer is laid at 1 in 600 slope. The diameter of the sewer is 150 centimeters. Assume n is equal to 0.015 in Manning's formula, and that the sewer is running half full. So, first of all, I would like to note here, in all of our lectures, the slides have the small n, not capital N, right? So, just a small thing to note so that there is no confusion. And we are supposed to be answering the following questions based on the above data. So, question number 3 is, what is the velocity of flow in the sewer? Right. So, as we can see from the slide, we'll be using this Manning's equation for gravity flow. You note here the profile of the sewer is not actually given. I know diameter is given, but that doesn't necessarily mean that the sewer is circular. So let's go for the generic Manning's equation formula for gravity flow. Circular sewers will have this particular equation, but we'll be using this one for our current calculation, right? So we'll be needing uh, three values. Okay, we have one answer, 1.4. We'll work out the problem, Mr. Rahul. We'll see what the answer comes out to be. So and thank you for working on. So n is the Manning's coefficient, or the Manning's rugosity coefficient. R is the hydraulic radius, or the hydraulic mean depth of pipe in meters. If you remember, hydraulic mean depth is the area of flow. So if this is a pipe, and this is the water flowing, right? So this is the wetted perimeter, right? And this area is the area of flow, as in how much of the pipe is covered when it cross sectionally when there is sewage flowing through. So the hydraulic radius or hydraulic mean depth of pipe is essentially this area of flow divided by the wetted perimeter. So it's wetted. I've seen a few students take it as weighted perimeter, which is why I'm sort of, how much of the perimeter gets wet is the basis, right? So what are we given? We're given that the sewer slope is 1 is to 600, which will be taken up as 1 divided by 600. Sewer diameter is 150 centimeters, which is equal to 1.5 meters. N value, as I had said, we are going to take it as small n, because that's what's given in the lecture, is 0.015, and the sewer is running half full. Right, what are we supposed to find? We are supposed to be finding the velocity of flow, and we'll be using Manning's equation for calculation. So solution is pretty straightforward. We first calculate the hydraulic radius, which is equal to flow area divided by wetted perimeter, right? So the flow area is, since it's half, actually there has to be another half here. Half of the circle is being used, so we'll be using, sorry, that is missing here, and divided by the wetted perimeter. The wetted perimeter is taken as half. So usually the perimeter of a circle is 2 pi r, right? But we are taking here pi r, r is equal to d by 2, right? And this is, since half the sewer pipe is full, we'll be taking half of the flow area. So the simplifying this, the answer comes out to be d by 2, right? So, and the answer is 0.75, if I'm not wrong. So let's substitute the values in Manning's equation. It turns out to be 1 divided by n into r power 2 by 3 and s power 1 by 2. And substituting the values, n is actually 0.015 as given in the question. R is 0.75 to the power 2 by 3 and S is 1 divided by 600 power 1 by 2. The answer actually comes out to be 2.25 meters per second. Now that I think about it, I have a suspicion that they probably did not take this divided by 2 into consideration. So these are solutions provided by the NPTEL team, right? So, yes, ma'am.
Actually, hydraulic radius is d by 4, right?
Yeah, yeah, I'm wondering. One second.
Could you please check?
I'll just check the previous year's solutions that they were.
Even from lectures, you can find. I
Yeah,
remember
yeah. I
it
mean,
was.
I told you, no, that it's supposed to be by 4, which is why I'm wondering if they've given the right answer.
Okay.
One second.
It's d by 2.
It's
How?
actually d by 4. They've made a mistake, right? So, which means the answer here will also be. Let's calculate. Let's directly calculate instead of me taking the answers from them. So here it will be another divided by 2, right? Because this is the area pi r square divided by 2. So we'll have d by 8 and here d by 2, so it will be d by 4. Yes, which means our radius will also subsequently change, right? So 1.5 divided by 4 gives us 0.375. So substituting this value and not the former value, right? So actually, let me do it in Excel. It's easier for me as well. It's 1 divided by 0.015, then 0.375 to the power 2 by 3. And this is 1 divided by 600 to the power 1/2, right? And we shall be multiplying. Yes, so the answer is actually 1.4153. Yes, so Mr. Rahul, you are correct, and I guess we'll have to. I'll let the NPTEL team know, right? So that will be our answer. Is this all right now, ma'am?
Yeah.
Yeah. Okay.
I have not checked the solution, but by process wise,
No,
it
no.
is.
This has to be the answer, and I'm glad that Mr. Rahul also has the same answer. I guess we
Okay,
are in
then.
the right, but at least the process is right. The this is the hydraulic radius. It's not d by 2. So
Yes.
I'll request the NPTEL team to also change it in the original solution provided. Alright? So yeah, so the moving on to the second, what is this discharge flowing through the sewers? We'll have to again probably modify it. So when we are taking the discharge through the sewers, we can't, because the flow is half. We can't directly assume that it's half. Matlab, if the flow is say 3/4 of the sewer, we can't assume that the flow will actually be 3/4 of the value of the total flow, right? If you remember, proportionate discharge could be higher and velocity could be higher than the full velocity, velocity at full flow, which is why here we are just cross checking for the halfway point. It so happens to be half, right? The when the sewer is half full, the proportion is also half of the flow, right? Therefore, okay, here again, is 0.4153 if I'm not wrong. Right, the calculation will vary. Let's solve it together. So the flow will be zero point 0.5 times A into V. So that will be zero point 0.5 times pi d by 2 square into V. So there will be zero point 0.5 into the d is 1.5, yes, but V value is 1.4153, right? So let's calculate this as well. So that will be zero point 0.5 into 2.14 into 0.75 square into 1.4. So this will be, so our answer will be 1.2499. So 1.25 essentially, not 1.99. Right. So I'll ask the team as well to modify the solution. So these are the two values, right? The original solution that has been suggested is 1.99, but that's not the answer. Please take note of this. Any queries in the formula or anything?
No.
All right, it's a straightforward substitution, except the wetted perimeter calculation was wrong here. I'm sorry about that. So moving on to the next question. This is again a set of numericals based on the values given. Right. So consider the following data. Circular sewer diameter is 50 centimeters. Slope is 1 in 220. So that is 1 is to 220, or 1 divided by 220. And the n value, again, it's given as capital N, whereas all our formulae use small n. Please be mindful. Which is the Manning's coefficient is 0.015, and the flow is considered to be full this time, right? So, and we're supposed to be solving three questions based on this data. First question is, what would be the velocity and discharge of flow in meter per second and meter cube per second respectively. So this is again using the same process. We'll be using Manning's equation for gravity flow, right? So this is a given data. We have a diameter of 0.5 meters, sewer slope is 1 is to 220, n is 0.015, and sewer is running full. We need to find the velocity and discharge of full flow, right? So using the same process that we used before, this time I guess the area will be correct, right? So here it's pi r square, and divided by wetted perimeter is 2 into pi into d by 2. So however again d by 4, yeah, here the hydraulic radius is d by 4, right? So thus we, the diameter given is 0.5 meters divided by 4, and that gives us a hydraulic radius of 0.125 meters, right? So now substitute the value in Manning's equation. That gives us 1 by n into r power 2 by 3 into s power 1 by 2. So the n value we substitute 0.015 into r value is 0.125 as we have just calculated, and s value is 1 by 220, and the answer turns out to be 1.124 meters per second. I'll just check now that the answers seem to be very shaky. So 1 divided by 0.015, this is 1 to 5 to the power 2 by 3, and 1 by 220 to the power. Then we multiply all of this. So answer comes out to be 1.1236. 1.12. Mr. Rahul, I don't know which value is differing for you. You've gotten 1.116, right? Please check, and if there is a discrepancy, please let me know, right? So, okay, decimal rounding. That's fine. That's fine, I guess. Usually, what we try to do is, even for examinations, we try to keep the intermediate values to 4 decimal points, and then the final value we move it off to round it off, if any. So, just keep that in mind. It shouldn't be such a big deal, right? So, this is our answer for V, and for Q, again A into V. So, we are taking the full. Since sewer is running full, we are taking the formula for full flow, full discharge. So the area is pi d by 2 the whole d by 2 squared and into V. So it turns out to be this is the answer we got in the previous step, right? So it turns out to be 0.22 meter cube per second, right? So that's our answer, and we can see this answer. I guess you would have also selected this answer, Mr. Rahul, because it's the closest value possible, right? Yeah, all right. So that's the solution for the first question. So here we had the value to be so and so for the flow being full. However, the next question goes on to question as to what would be the velocity and discharge when the same is flowing at zero point 0.3 of its full depth. Right now, we look at this chart and we realize that the proportionate depth that we are talking about is zero point 0.3 of full flow, right? So here, in order to calculate the velocity and the discharge, we'll be using this proportionate velocity and proportionate discharge, right? So these are the values given, and we'll be using the values from the table. So the solution is proportionate velocity is, it is for a small v. So this is for zero point 0.3 flow, right? And this is for full flow. So the given number is 0.776. That implies that we basically cross multiply, right? So v is small v is equal to 0.776 into capital V, and that gives us an answer of 0.776 into 1.124. Yes, yes, Mr. Rahul. V by V as 0.776, right? So the answer turns out to be 0.872. Similarly, in case of proportionate discharge, what we do is Q by Q is equal to 0.1956. So that is again given in the table, and then we cross multiply, right? Take this Q value, and that turns out to be 0.22 from the previous calculation, and the answer is 0.043 meter cube per second, right? The solution is B, 0.873 and 0.0. Similarly, when we are looking at the flow at zero point 0.7 of full depth, we'll take the values for uh, zero point 0.7 of the proportionate depth. So the values turn out to be 1.12 for V by V and 0.7258 for Q by Q, right? So these values are usually given. In proportionate velocity, we do the same thing. V by V is 1.12, so V is equal to 1.12 into capital V. And the capital V, we had calculated it to be 1.124, right? And the answer turns out to be 1.259. For proportionate discharge again, Q by Q is equal to 0.7258. Q is equal to 0.7258 into capital Q, and that turns out to be 0.160 meter cube per second, right? So our answer is C. Any queries in this numerical?
No.
Alright, alright. So let's move on then. Going on for a theoretical question. The dash of a storm event may be defined as the average recurrence interval between events equal to or exceeding a specified magnitude. So, any answers? The average recurrence interval between events equal to or exceeding a specified magnitude. So if we look at the slides, this is for the return period selection as has been mentioned in CPHEEO manual 2019, right? So that's a direct answer from the slide. So the answer is return period. So the return period of a storm event may be defined as the average recurrence interval between events, which is equal to or exceeding a specified magnitude. Alright. So the next question. Return period selection of a storm depends on A. Importance of the drainage area, B. Socioeconomic conditions, C. Constraints, that is funding and availability of space, and D. Design period of infrastructure. This answer is again in the same slide actually. So this value actually depends on the importance of the drainage area, socioeconomic conditions, and constraints of funding and availability of space. Right? So again, a very direct answer. The answer is A. Because essentially design period of infrastructure is not really going to influence the occurrence of a storm, right? The storm will occur. The infrastructure might influence how we respond to the storm or how much damage happens, right? Moving on to the next question. Sorry. So we essentially have a match the following. For inlet time, time of travel, time of concentration, and partial area effect. Uh, any answers for inlet time or the overall answer also? Okay, let's just go on and take a look at the slides. So we first look at the time of concentration. So the time of concentration has been specified as the time required for water to travel from the furthest point in the total catchment to the point of concentration, right? So the intensity of rainfall will basically vary as per the time of concentration. So that's our answer. And partial area effect is the maximum flow or peak discharge which may occur when only part of the upstream catchment is contributing. So this is something that we already spoke about in the last lecture also. So whenever there is a catchment area and there are points of inlet, right? So say this is the entire watershed and the topography permits all the water here. So these are the inlet points, right? all the water here to enter this inlet, all the water here to enter this inlet, and all the water here to enter this inlet. So we might expect, okay, for this point we'll also have water coming in through the pipe, and this point all of the water, so which is essentially all of the water from this entire catchment area will be going through here, right? Usually we'll expect this value to be bigger than this value. However, partial area effect might result in this value might being bigger than the whole catchment area. It depends on permissibility and etc. Right? So the next one is inlet time or surface or overland flow time is the time required for the rain in falling on the most remote point of the tributary or catchment area to flow across the ground surface along drains or gutter to inlet of sewer. Right? And the time of travel is the time required by storm water in traveling from the uppermost inlet up to the point of concentration. So there we go. Our answer will be A. So inlet time is the time required by runoff from the most remote point to inlet of server, which is the point of concentration, right? So Q will be 1. Time required by storm water in traveling from uppermost inlet up to, yeah, point of concentration. Time of concentration is 4. Time required by runoff from the most remote point of the catchment to reach the point of concentration. And partial area effect, as we said, is maximum flow, while part of the upstream catchment is contributing. Any questions here? These are all definitions that need to be sort of remembered for your exam as well. These are basic concepts that you need to know, right? Alright, moving on to the next question. Runoff entering into the sewer depends on A. Imperviousness of the catchment, B. Shape of the drainage area, C. Duration of storm, and D. Specific yield. Any answers? We have one A. The answer is actually right. So we have this again directly from the lecture contents. Within the imperviousness of the catchment area, essentially these are influential points, right? You also have shape of the drainage area and duration of storm. So the answer is A. Specific yield does not really determine the runoff entering into a sewer. Right? So let's move on to the numerical. Any doubts till now? I hope not. These are all theoretical questions directly from the lecture, right? Okay, so moving on to the last numerical. So here actually there is a, this is the question that I was talking about, that there is a discrepancy. It looks like this is the second question where we have a discrepancy for the evening. So yeah, so determine the minimum required diameter of a circular sewer making use of the following data. So area to be served is 120 hectares. So that will be into 10 to the power 4 meter square, right? Hectares to meter square. So 1 hectare is equal to 10,000 meter square. Just remember this always. Pardon my bad handwriting. So, and population of the locality is 30,000. Maximum permissible velocity is 3.4 meters per second. Time of entry is 5 minutes and time of flow is 20 minutes. The rate of water supply in the area is 230 liters per day per capita, so IPCD. And impermeability factor is 0.45, right? So one thing that we need to remember here is the time of concentration is equal to inlet time into time of travel in the drainage system, that is time of flow. So if you look at the question, they have given it as time of flow, right? So uh, I'm sorry about. I just ignore. I hope you understand that's a mistake. So these are the givens, and we need to find the minimum required diameter of the sewer, right? So we'll be using for intensity calculation. We'll be using the empirical formula for rainfall intensity. First of all, let's calculate the quantity of water supply. Before that, that will include population into rate of water supply, right? So how much population is there, and rate of water supply is given per capita. So that will be 30,000 30,000 into 230. 230 is for the entire day, which means our calculation will be looking at per second. So therefore we divide it by 24 into 60 into 60. So this is the LPCD, and this is to convert it to per second. So the answer apparently comes down to be 133.10. Let's check that as well. So we have 30,000 into 230 divided by 24 into 60 into 60. So there is a small error here as well. Or am I reading the question wrong? Okay, so there is a minor error here also. I think there was an issue in translating between the original question and the modified question. So right. So the answer is actually 79.8611. Let's just do this calculation, right? So then we have maximum discharge, which is usually 1.5 times the average discharge. So we always design the sewerage network not for the average flow, but for the maximum flow, right? So we take 1.5 into 79.8611, which turns out to be 119.79. 7917 liters per second, right? And in order to convert this into cubic meters, we need to divide it by 1000. So that makes it 0.1191179 cubic meters per second, right? So that's our calculation of maximum discharge. But why are we calculating maximum discharge? Essentially because this flow almost completely will end up being calculated as the from the sewage from the household, right? The input from the households and all the houses into the sewerage network. So this is our sort of proxy for the amount of sewage coming out of the households, right? So this. So now we calculate the intensity of rainfall. For that, we need to take the time of concentration for what duration, which will be inlet time into time of travel. If you remember from the lecture slide, right? Which turns out to be 5 minutes. Time of entry is 5 minutes, and time of flow is 20 minutes, right? So that turns out to be 25 minutes. So thus we use the empirical formula for rainfall intensity, which is this one, right? I is equal to 25.4 into A divided by T plus B. So here A and B are coefficients that are built into the empirical formula, and T is the time of concentration, which we get from this calculation, right? So right now we see that the time of concentration is 25 minutes. So A and B's value varies when the duration varies. So for right now we have 25 minutes, which is more than 20 minutes, right? When the duration of storm is 20 minutes to 100 minutes, the value of A is 40 and B is 20. So we substitute these values. So we equate A to 40, T is 25 and B is 20, which hopefully turns out to be 25.578. So it's 25.4 into 40 divided by 45. So yes, 22.578. Next, the peak flow estimation, we usually use this to be Q is equal to 10 into C into I, right? So, however, the original rational formula is 360, CIA divided by 360, and they have used this formula. I'm not sure as to why there is a digression. So we usually use this for stormwater calculation, right? However, I'm going to go ahead and retain this calculation, right? So here what they've done is Q is equal to C into I into A divided by 360. That's the original rational formula. So that turns out to be 0.545. It shouldn't technically vary so much, but let's see. So 0.45 is the C value, impermeability factor value given, and 22.578 is the I that we just calculated, right? Then we have 120 divided by 360, which turns out to be 3. Okay, so if I'm not wrong, the difference between the two is the this value has been taken as, I'm not sure why there is a difference, right? So I'll this is the part where I told you I'll get back to the NPTEL team. I'm not really sure why the calculation is varied. So according to their calculation, it is coming out to be 1.2 meters. So we basically take combined discharge to be 0.1997, which is the value from the one second, just Google, which is this value for us. 1179 is what we are getting, right? And 25.578 is what we are getting. So using that, the value will vary largely, but I'm going to stick here. So originally what we do is we use the combined discharge as to we get the discharge from the rational formula as well as the discharge from the uh, quantity of water supply, which is the sewage discharge. So this is sewage and this is storm water, right? So then we multiply as Q is equal to A into V, and then area of the sewer will be discharge divided by velocity. Velocity will be limited by the maximum velocity permissible in the, so this is the maximum velocity permissible in the sewer, right? So that's 1.055. So the diameter of the sewer turns out to be, like calculating back from the area, 1.16 meters. And Mr. Rahul has sort of gotten almost the same, right? But there seems to be a discrepancy between what has been calculated by Sir and what has been suggested by the team. I'll get back to them and I'll resolve this issue and post the final solution in the discussion forum. Please pardon this discrepancy. At least I will be explaining the as to why two different formulae have been used. But that being said, that's the answer for the question, right? Any major doubts apart from this issue in the solution? The basic steps are going to remain the same. We'll be looking at the quantity of water supply, and we'll be taking the maximum discharge as 1.5 times or 1 point whatever value. If there is a value given, if they say that it has to be 1.8, then you take 1.8. Then we will calculate the maximum discharge. So this will be the sewage, right? Yeah, both formula are getting the same answer, but if you remember there was a mention that we usually use the 10 into CA. So I'm not able to figure out where the difference is. That is why I'm saying I'll end up getting the answer from the team and I'll post in the. But yes, both ways you will end up getting an answer close to 1.2 meters, right? This is similar to the population projections where we take the initial value and then there is another value. So please pardon the small confusion, but why the process will be the same. We'll be then calculating stormwater by figuring out the time of concentration and the intensity of rainfall, and then we go for rational formula. We get the combined discharge, which is sewage plus stormwater. We add the two values, and what we do is we take the q is equal to a into v, and then figure out the area, cross sectional area of the. So this is the cross sectional area of the sewer, right? And from this we derive the diameter, which turns out to be 1.2 meters, right? All right. So if there are no questions, we are actually done for the day. This first question I will post the modified answer as well, right? Any other general queries? All right. Thank you. Thank you then. Have a good night.